Hi, welcome to another tutorial video in which I'm going to be explaining the half adder and the full adder logic circuits. Let's think back for a moment at binary addition then, and these are our basic rules for binary addition. And if I do this binary addition that I've got set up down here, first of all I can use the third rule, 0 plus 1 equals 1, 1 plus 1 equals 0, carry 1, 1 plus 1 equals 0, carry 1, and 1 plus 1 equals 0, carry 1. And obviously I've got an overflow error here, but this is basically just a reminder of the basic rules of binary addition. The half adder and the full adder logic circuits are how logic circuits in computers actually perform this binary addition. And this is the logic circuit diagram for a half adder. So we've got two inputs A and B and two outputs S and C. And our inputs A and B are the numbers in our addition here, so in this case 0 or 1. So let's just run through this as an example then. Let's have A as 0 and B as 1. And our outputs, S is the sum output, and the sum output is what we would have in between our lines here, so the so this number here, and the C is the carry output, so it will be 0 unless there's a carry bit there. And if we follow the path of A and B then, so A is going to be 0 here and B is going to be 1 here. Let's look at the Xor gate first, so ignoring the AND gate for a moment, let's look at the Xor gate. So here we've got 0 and 1. If we do an XOR on that, that's going to be 1, so our sum bit is 1, as we've got here. And if we follow A and B down here to the AND gate, 0 and 1, if we perform an AND, logical AND on 0 and 1, that will give us a 0. And we can see that's what we expected to get, because we used this rule here, 0 plus 1 equals 1. And that's what our half adder logic circuit has given us. So let's look a bit at the truth table for a half adder then. We've got two inputs A and B, and we've got two outputs C and S. And if our inputs A and B are 0 and 0, our sum output here is going to be 0, because we're just using our rules of binary addition, 0 plus 0 equals 0. And our carry bit is also going to be 0, because we're not carrying 1 as we are with the last rule here. If our outputs A and B are 1 and 0, our sum bit is going to be 1, because we're doing 1 plus 0 equals 1, and our carry bit is still going to be 0. If our outputs A and B are 0 and 1 again, but just the other way around, it's going to be the same. So our sum bit is going to be 1, and our carry bit is going to be 0. And if we our inputs are A and B are 1 and 1 again, then our sum bit is going to be 0 this time, because our sum here, when we use the 1 plus 1 rule, is 0, and we carry 1. So our carry bit is going to be 1. And that's the truth table for a half adder. Okay, so we've had a look at the half adder. I'm now going to take a look at the full adder. For your A level, you don't need to be able to draw or recall the full adder logic circuit. You only need to be able to recall the half adder logic circuit, the half adder truth table, and the full adder truth table. So the difference between a half adder and a full adder is the full adder also takes account of values that are carried into the calculation as well as the carried out. So with the half adder we had a carry output. With the full adder we've got two inputs, A, B. We've also got a carry in, so we've got C in, and we've also got C out and our sum bit, as with the half adder. So What we can do then is we can work out our truth table for the full adder, and this is just going to be exactly the same as working out it for the half adder. We're just going to use our rules of binary addition, but we're going to need to take account of the fact that we might have a carry bit, so we might have a carry in like we've got in this binary addition here. So say first, for example, that A and B are 0 and our carry in is 0. If we've got 0, 0, 0, our sum bit is going to be 0, because it's just 0 plus 0 plus 0 equals 0, and our carry out is going to be 0. Then we could have 0, 0 and 1 for our carry in, and that's just going to be the same as doing 0 plus 1 equals 1, so our sum bit is going to be 1, and our carry out is going to be 0. And then we could have 0, 1, 0 as our inputs, and in that case it's just the same as the previous case. We're doing 1 plus 0 equals 1, and our carry out is going to be 0. Then we could have 0, 1, 1. In this case we are going to have a carry out bit because we're doing 1 plus 1 equals 0, so our sum bit is going to be 0 and our carry out is going to be 1. Now we could also have 1, 0, 0, and that's just going to be exactly the same as our previous two up here where we only had 1, 1 as an input. So we're going to have our sum bit being 1 and our carry out being 0. Then we could also have 1, 0, 1, and that's going to be the same as this one here. Our sum bit is going to be 0 and our carry out is going to be 1 because we're using this rule here, 1 plus 1 equals 0, carry 1. And then we could have 1, 1, 0, and this is going to be the same as this one. A sum bit is going to be 0 and our carry out is going to be 1. And the final permutation of inputs that we could have is 1, 1, 1. And that's going to be 1 plus 1 plus 1. And for that one our sum bit is going to be 1 and our carry bit is going to be 1 as well, because we're doing 1 plus 1 plus 1 equals 1, carry 1. Okay, so that's the full adder truth table. You're going to need to be able to work that out, but if you follow the rules of binary addition, you should be able to work that out pretty easily in the exam. The difference between a full adder and a half adder is that with a full adder we've got 3 inputs, and one of them being this carry in, so we can deal with calculations like this one, 1, 0, 1 here that we've got in this example binary addition. So half adder only has 2 inputs, A and B, and 2 outputs, carry out and sum, the same as the full adder. Okay, so I hope you found this summary of half adders and full adders useful. Thanks for watching.